Welcome, everyone. Thank you so much for coming along to this very special lecture. And it's really great to see so many of you in the room here, so many faces that I know from all different walks of mainly physics, science, and strangely enough. So my name is Professor Virginia Kilbourne. I'm the Chief Scientist here at Swinburne. I have been the Department Chair of Physics and Dean of Science in the past, where I know many of you from as well. And so we're really glad to be here to celebrate Peter and listen to his latest research today. Before I get onto the actual introduction, I'd just like to let you know some housekeeping. We're going to do a Q&A after the presentation, so get all those tricky questions ready for Peter, or the not so tricky ones as well. And if you're online, welcome, and please feel free to put any questions that you'd like into the chat. I'll have an iPad that has the questions on there, so I can read them out from there. And for people in the room, we'll have a microphone. So when we get to that part, just remember to use the microphone and let us know who you are before you speak. So that's all about the Q&A, but obviously we're here to introduce distinguished Professor Peter Hannaford. And it's really difficult to provide a comprehensive biography of Peter and still actually have time for him to speak as well. So I've just condensed it very, very short, but just a few words about Peter's career. So Peter did his university education at the University of Melbourne, including a Bachelor of Science, Masters of Science and PhD. And then he was a chief research scientist at CSIRO in Clayton before the move to Swinburne in 2001, which was, I would say, a very big coup for Swinburne at the time, and subsequently to become director of the Centre for Atom Optics and Ultrafast Spectroscopy, where Peter has remained, although the centre has changed a little bit. Peter's research centres on laser spectroscopy and atom optics. He's used tunable lasers to understand the spectroscopic properties of atoms and conducted pioneering research on Bose-Einstein condensates. And more recently, and what we're going to hear about today, is he's worked on time crystals, and this research is supported by an ARC grant. Peter's been, as you can imagine, a visiting professor all over the world, including the University of Reading in the UK, Griffith in Brisbane, University of Otago in New Zealand, University of Oxford, Max Planck Institute for Quantum Optics in Garching, Germany, the European Laboratory for Nonlinear Spectroscopy, Florence, Italy, the École Normale Supérieure in Paris, sorry for my accent, and the University of Innsbruck in Austria. He's won many, many awards, as you can imagine, including the Walter Bose Medal from the Australian Institute of Physics and the Royal Society of Victoria Research Medal. He became a Fellow of the Academy of Science in 1991. What we're really celebrating here today, of course, is Peter's award as a Companion of the Order of Australia Medal this year, which was in recognition of his eminent service to science, particularly to experimental physics, as an academic researcher to professional institutions and as a role model for young scientists. And I think we can all really reflect and understand why Peter received this honour from the highest levels in Australia, because every one of us here has been touched in one way or another by Peter's warmth, generosity and brilliance in his research. So we're really happy to be here to celebrate your achievements today, and most importantly, find out what is a time crystal and what are you doing with them. So I'll hand it over to you, Peter. Thank you.
Thank you, Virginia, for those very kind words. I'd like to start by acknowledging the various people I've worked with over many years. And this is a list of them, these both students and collaborators. And I hope I haven't missed anybody out. So in just over 60 years now, Ted Maiman shocked the world by announcing the operation of the first laser. It came as a big surprise. He worked at Hughes Research Labs, and he didn't have, he worked on a shoestring budget. He only had one assistant, and he didn't have any support from Hughes itself. So this occurred in ruby laser, in red ruby laser, and it was in a little laser, a little device like this. And when Hughes had a press conference to announce the new laser, new death weapon, the laser which actually worked was this little one here. And the publicist for Hughes said, oh, this is not very impressive. Let's try this one, which had never been used as a laser. So the official photograph is this big one here, which wasn't actually a laser. And Ted Maiman submitted his work to PRL and was rejected, and he had to settle for nature. He was also the person, I didn't realize this, the person who said the laser is a solution seeking a problem. And within 12 months of him announcing the laser, Peter Franken showed for the first time that you could start off with red light from the ruby laser, send it through a nonlinear crystal, which was quartz, and you come up with ultraviolet light. So you're going from 694 nanometers down to 347 nanometers. And if you squint and look very closely, this is the red light. You can just see the UV light, but if you can't see it, I'll zoom in on it. We zoom in, and you still have to squint very, very hard. It turns out when this paper was submitted to PRL, the printer thought this was a defect and removed it. And so the paper actually is like this, without the second harmonic generation present. A very nice story. So the next thing Peter Franken did, just 1 year later, was he bounced light from the moon. This is all within 2 years of the first laser. And I think this demonstrates that the problem is solving, that it's a problem solving solving things that are very important. And not so long after that, Neil Armstrong placed an array of corner cubes on the moon to reflect the ruby laser beam back to Earth in about a second. So this shows the corner cube, which is cat's eyes, placed on the moon. Okay, so the real excitement came in 1966 when Peter Sorokin, IBM, produced the first tunable dye laser. Before that, the wavelength, the color of the lasers were fixed. But to do any spectroscopy, you need to be able to tune in to the wavelength of the atoms or molecules. And so this came in 1966. This coincided with the time when I finished my PhD and I was starting a new position at CSIRO in Clayton, Division of Chemical Physics. The chief was Lloyd Rees. And I was very fortunate to be in the spectroscopy group of Alan Walsh, or Sir Alan Walsh. He became famous for the method of atomic absorption, which revolutionized elemental analysis in the 1960s. It provided a very quick and accurate method for analyzing almost any element, a very quick and accurate and very precise method. So you start off with the sample is dissolved into a liquid here, sprayed into a high temperature flame, and light from a hollow cathode lamp of the element you're studying is absorbed through here. And the amount of absorption tells you how much of the element is present. So Alan suggested that I might look into another way of generating these atomic vapors instead of using a flame. would it be possible to analyze a solid sample directly without having to dissolve it into solution? And the method used was to use cathodic sputtering, where you have the element of interest is made the cathode of a rare gas discharge. It might be argon, for example, and argon ions formed in the discharge bombard the cathode surface and eject atoms, in this case, say, zirconium, from the surface to produce an atomic vapor. Now, this is a universal method. It applies to almost any element in the periodic table, including these highly refractory elements here, which are very, very difficult to vaporize by thermal methods. And we looked into producing an instrument that you can just put the sample on top, a solid sample, might be an alloy, and you measure the absorption from this hollow cathode lamp. It worked nicely. We had it commercialized, and people in Oregon Corporation, Analyte Corporation in Oregon, they engineered it to make it look fancy and work very nicely, and sold these off. Unfortunately, it didn't really take off because the flame was still very, very popular. And so we thought, okay, lasers have now come on the scene, so let's use this method of vaporization to do laser spectroscopy, essentially any element in the periodic table. So this is our first tunable laser, tunable dye laser, which was pumped by a nitrogen laser. It was an electron, 4 nanosecond pulses, and you could tune anywhere from about 260 to 900 nanometers over a very broad range. So the first thing we tried to do was just some time-resolved fluorescence on zirconium, which is a highly refractory element. This shows just a single-shot decay curve. You take the logarithm and just plot it, you get a lifetime of 123 nanoseconds, about 2% accuracy, and we get the lifetime out in less than a minute. And so we could study a lot of levels and a lot of elements very, very quickly. Lifetimes, of course, are very important for producing absolute transition probabilities, which are very important for all sorts of science, including astronomy. I'll talk about that later. So this just shows some of the systems that we measured atomic lifetimes in, a fair sprinkling of the periodic table. After about 1990, we got sick of doing this. We moved on to the next project. But in the meantime, Jim Layler came along from Wisconsin, and he filled in the rest of the periodic table almost for us. He took another 30 years. He still do, in fact, he passed away, unfortunately, just a few months ago. He spent his whole life on this, using the same method of sputtering. And then, of course, atomic transition probabilities, precise ones, are needed for solar abundances. And I was working with Graves from Liège, Nicolas Graves, who analysed the solar atlas, the Jungfrau-Joch solar atlas for various elements. And the elements in red are the ones that we investigated, and the yellow ones are the ones Jim Lawler did. And we essentially rewrote the abundance table with very, very much higher accuracy. And why we could do this to such high accuracy is we could obtain these, we could measure these lifetimes very, very quickly. In less than a minute, we could do a whole element in a day, maybe 50 different levels. And then with the solar, when determining the solar abundance, you plot a curve for a whole lot of different transitions. And if there was an outlier, that would mean there'd be a blend in the solar atlas, and you could discard it and so on. And this way we get very, very accurately the solar abundances. Again, we got sick of that, moved on. But we're very interested to see whether we could do coherence experiments. And here, this shows ytterbium in a magnetic field of 1.7 Gauss. You have polarized laser light coming in, it's the magnetic field. The direction of polarization rotates and you see a quantum beat, a beautiful quantum beat. This is a 0 to 1 transition, which means that theoretically you can get 100% visibility. This we use so the coherence is preserved apart from the rare gas, which is present, and that's what you're trying to measure. And you can get magnetic moments from the period of the beats. And this is these are excited state quantum beats or Zeeman beats. We can also do ground state ones, and samarium has a very nice 1 to 0 transition, which is sort of a lambda transition where you can produce coherences in the ground state. And this shows, this is experimental data, this shows the beat pattern for ground state quantum beats, in which you can measure the magnetic moments and depolarization rates very precisely. So the next step was to go from pulsed lasers to CW lasers, which came on the scene somewhat later. And we wanted to be able to do a Doppler-free saturation spectroscopy experiment. So here you send one beam in to your sputtering cell, your vapor here, and you beam split and send a second beam in the opposite direction, so that both beams only interact with those atoms with a 0 velocity component in the plane perpendicular to the laser beams. So the atoms are interacting with both beams. In order to do that, they must have a 0 velocity component. They don't have a 0 speed, but a 0 velocity component. Again, we chose zirconium, and this shows if you use just a single beam, the absorption spectrum, which is the Doppler broadened spectrum. It's still very narrow, it's only about 1 gigahertz or less. And now when you use 2 beams, counter-propagating arrangement, you can see the full isotopic structure and the hyperfine structure. With the different isotopes here, this depends on the mass of the isotope and on the charge distribution of the nucleus in that particular isotope. While the 91 being an odd isotope, you can see the splitting, hyperfine splitting here. So the method of saturated absorption selects out atoms with 0 velocity component along the laser direction. Can all the atoms now be slowed to near 0 speed? Not just the velocity component perpendicular to the laser direction. Can all the atoms be slowed? And in the 1980s, the idea was suggested first by Hensch and Shallow, where if you detune the laser field pointing towards an atom, then if you detune it to the red side, the atom will only absorb the light. Only atoms moving towards the laser will absorb the light. And so if you allow, say, 1,000 photons or something to hit the atom moving towards you, it's like throwing 1,000 ping pong balls at an army tank or something. Eventually you'll slow it down. As well as that, the atom will re-emit light in all directions, and that'll start to heat it up again. So there's a limit we call the Doppler cooling limit, which is about 100 microkelvin. And then Bill Phillips discovered in 1988, he found that you can get temperatures much below that. You get about 10 microkelvin. So it was colder than theory. This is a gross violation of Murphy's law, which is very rare. And the theorists then came along and said, okay, we really have a multi-level atom system with so-called polarization gradients, which gives you light shifts, hills and valleys. These light shifts are position dependent. You get hills and valleys and what they call Sisyphus curling, where you climb up and down the mountain. This work was interpreted by Claude Cohen-Tenergy and Steve Chu with their groups. And as a result, they all won Nobel Prize. So the work going on here, we started in the early 90s with Jeff Opat, who was Melbourne University. This was a collaboration. And the idea was to use these cold atoms to try and bounce them from a mirror. And Jeff proposed this method of producing a mirror where you have alternating north-south, south-north magnets like so. If you analyze this, if you connect up the arrows, you see that the magnetic field direction is continually rotating as you go along here. And in addition, the magnitude of the magnetic field falls off exponentially with distance. And so if you prepare the atom in a positive magnetic state, it falls onto the mirror and bounces up just like on a mirror. So the experiment was Andrei Sidorov and Wayne Rowlands were involved in this early work. And the first work was done with cesium, and we saw 100% bounce, which was very encouraging for a first experiment. And then, of course, much better mirrors were made, and this shows a period of just 1 micron, which means it's a very hard mirror. It means the atoms bounce from very close to the surface. And for rubidium, and this shows the atoms bouncing. After a while, they warm up, they spread out due to the finite temperature, bouncing from 12 millimeters. From these sorts of mirrors, you should be able to bounce from about 2 meters. So at this stage is when our group moved to Swinburne. I moved a couple of years earlier than the rest of the group, and I was just spending 1 day a week. Anyway, at that stage, Swinburne was looking to enhance its research capability, and in particular, Ian Wallace was the Vice Chancellor, Dick Pratt was the Chancellor, and Dick, of course, was the boss at Visi, and he was the 2nd or 3rd richest man in the country at the time, and he really supported Swinburne very strongly in terms of new buildings and beautifying Swinburne. The idea was to try and turn Swinburne into a Caltech in the Southern Hemisphere. But of course, there's always a caveat, and Dick was wanting a Nobel Prize out of all this, which he hasn't got by this stage. This shows the opening of our labs. Ahmed Zewail was invited to come and open it. Ahmed Zewail from Caltech. This shows him with Ian Wallace. So it was opened in 1999, and Ahmed was made he received an honorary doctorate from Swinburne, and later that year he received the Nobel Prize in chemistry. So one of the prerequisites for being awarded a Nobel Prize is to be awarded an honorary doctorate at Swinburne. So this is the group after a few years. There's a few suspects here you all recognise. Won't go into them in detail. Brenton in the first row is here. Wayne Rowlands, Paul Stoddart, etc. Russell McLean, Andrei Sidorov, Brian. Okay. So during this time, we were involved. We were very fortunate to be awarded 3 ARC Centres of Excellence. First of all, quantum atom optics went for 8 years. Then coherent X-ray science went for 8 years. And then recently, there's the Fleet one, future low energy electronics, which is still going. So the first main project that was involved was to try and produce a Bose-Einstein condensate of ultra cold atoms on an atom chip. And this shows the atom chip where you can have either a U shape, which gives you a quadrupole trap, or a Z shape, which gives you what we call a Yoffie-Pritchard trap, which means you don't have zero minimum magnetic field. And this is important when you go to very low temperatures, so you don't lose all your atoms down the plug hole. So this is the current for the Z wire trap. This is the current for the U trap here. And we apply a bias field to produce the trap. These are the people involved. But I better just say a little bit about Bose-Einstein condensation. This is a cartoon Wolfgang Gettley produced. So atoms at, say, room temperature behave as little billiard balls, flying around like this. As you drop the temperature down to very low temperatures, they start to behave as wave packets with a de Broglie wavelength given by Planck's constant divided by the mass and the velocity. And then when you go to very low temperatures and you compress the atoms, the atom cloud, so that these little wave packets all start to overlap, you then get a Bose-Einstein condensate, which is, this happens for bosons. And then as you go to very, very low temperatures, you get just a giant, behaves just as a giant matter wave. And it's a bit like soldiers marching in lockstep, where all the waves are just behaving as one giant wave. So just to give you an idea of the degree of difficulty of achieving this, to go from room temperature down to a Bose-Einstein condensate, you get it's 18 orders, approximately 18 orders of magnitude increase in phase space density, where the phase space density is the Brawley wavelength cube times the number of atoms per cubic centimetre. So it's 18 orders of magnitude. And this, of course, also resulted in a Nobel Prize from Carl Wyman, Eric Cornell in Boulder, and Kettley at MIT. So coming back to our atom chip experiment, this shows BEC produced in a Z-wire trap on the atom chip. As you drop the temperature down by evaporatively cooling all the hot atoms off, so you're left with the cold atoms, which then re-equilibrate. As you increase, as you decrease the depth of the trap, make it shallower and shallower, it gets colder and colder until you have this Bose-Einstein condensate here, which has the shape of an inverted parabola. You say, okay, why parabola? Well, it's because you have a harmonic trap and it takes the shape essentially of the harmonic trap. So the next experiment, which was mainly involved with Mandeep Singh, was to produce a periodic magnetic lattice on an atom chip, in this case, a 10 micron period along here. And we can do this by having magnets like so. We actually did it by producing a structure on a silicon surface and then coating it with a magnetic material. This is our atom chip arrangement. And to monitor this, we looked at reflective absorption imaging, where we have the chip up here and we reflect light up here. And you'll see two images, one on the way up and one on the way down. And this is the site resolved image, where the mirror is in the middle and you get an image on the top and an image on the bottom. These different lattice sites are separated by 10 microns. We don't see them all perfectly because the surface was a bit contaminated by the rubidium on the surface, but it doesn't affect the magnetic properties. It only affects the optical properties. And so the idea was at 2 microkelvin, you saw a distribution, a frequency spectrum like so. This is when you remove the atoms by applying a radio frequency field to flip the spin so it's no longer, the atoms are no longer trapped. And then you drop the temperature down lower and you start to see a bimodal distribution until at 1.5 microkelvin until at 0.4 microkelvin, which is below the critical temperature for Bose-Einstein condensation, which is estimated to be 0.6, you see this BEC Bose-Einstein condensate appearing. This is using site-resolved radio frequency spectroscopy. And then that was just for one favorite lattice site, which was lattice site 38. But of course, we detect all the lattice sites, and when we analyze those, we plot the temperature, the trap bottom, condensate fraction, the number of atoms per lattice site, and we get remarkably uniform distribution. The fluctuations here are mainly statistical. The trap bottom is very, very constant across. Okay, so we now have an array of about 100 Bose-Einstein condensates trapped in a 100 micron period lattice. But at this period, the tunneling times between the lattice sites are still very long, too long to do very much with it. So how can we get the BECs to talk to each other from neighboring lattice sites? To do this, we need periods of submicrons, excuse me. Okay, so this was some work, Saulius, Stuart Karzis, and student Amanda Balsaitis prepared a beautiful structure here, which is a structure needed to produce a triangular lattice. The period here is just less than a micron, it's just 0.7 microns. We have something like 1 million lattice sites. We use 8 atomic layers, bilayers of cobalt palladium with just atomic thickness. And this enables us to have very small grain size and to produce very high very precise structures. And if we look at the lifetime versus distance from the surface, this shows the lifetime coming down, the lifetime of the trapped atoms in this 0.7 micron period triangular lattice. Down this end, we're now within about 100 nanometers of the surface. And this is really unknown territory. And we see this, the Casimir-Polder surface interaction starting to come in due to the quantum fluctuations. So in this region, it's very difficult to operate. So we're able to do various two-dimensional lattice structures, such as a square lattice from, this is the magnetic film and this is the magnetic potentials. Triangular, this is the magnetic film and magnetic potentials. We can also do a honeycomb lattice, although we haven't built one of these. So this has enabled us to create artificial periodic lattices in space. So the next question is, what about periodic crystals in time? And in 2012, Frank Wilczek proposed what seemed at the time to be a very crazy idea. He said, can a quantum many-body system exist that spontaneously breaks the time translation symmetry? In other words, goes from like this to an oscillating system and undergoes periodic motion to form a time crystal in analogy with the formation of a crystal in space. And this created a lot of debate, vigorous debate, and eventually it was culminated in a no-go theorem, which says that time crystals cannot exist in the ground state or any thermal equilibrium state of a quantum mechanical system. However, this idea inspired other people to propose similar ideas. And in particular, Krzysztof Sacha from Krakow showed that a periodically driven system, in other words, you start off with a driven system, can reveal spontaneous breaking of discrete time translation symmetry. In other words, symmetry can be broken to give a longer period here, to give what we call discrete time crystal that evolves with a period s times longer than the period of the drive. And he proposed an experiment in which you have a Bose-Einstein condensate of ultra-cold atoms bouncing on an oscillating mirror which is oscillating, such that the period of the bounce is an integer number of the period of the oscillation t, oscillating mirror. And this particular system enables you to have dramatic breaking of discrete time translation symmetry, where S, the ratio, can be 20 to 100 times, 20 to 100 times. And so these are now big time crystals. And with such a big time crystal, it should be possible to do condensed matter physics now in the time dimension because you've got a big enough lattice. Nearly all other work that's been done use spin systems, which can be either spin up or spin down. And so S is only 2, which is not really a crystal lattice for doing condensed matter science. So first of all, we'll consider a little bit of theory. Single particle case, which is very well known. So we have non-interacting atoms bouncing on an oscillating mirror here with a small amplitude, which is small enough so that you have a stable system. If it's too large, you have chaotic motion, and that's not what we want. And we have strong transverse confinement, which is indicated by these vertical dashed lines. And so, for example, for S equals 40 and lambda, which is the amplitude of the oscillation, if 0.2 in gravitational units, which is dimensionless, and we produce 40 stable resonance islands here. I've only drawn a quarter of them, so there's 40 of them going right out here. If the amplitude is too large, you lose the stability here, and you get chaotic motion. So these are the simple classical calculations for a single particle case. And now what we really want is the many-body case, where we consider the interaction between the bouncing atoms in the condensate. So we can apply the nonlinear Schrödinger equation, the Gross-Pedievsky equation, which is a mean field theory. And we consider two cases when the interaction between the atoms is less than a certain critical interaction. Atoms tunnel between neighboring wave packets. We've got 40 wave packets, tunnel between these 40 wave packets, just like in a temporal superfluid. Or you can have, if you have a larger interaction between the wave packets, this stops the tunneling and you get a superposition of S wave packets, which is like a Schrödinger cat state, which collapses into just one of the S wave packets. Any very small perturbation, of course, is. And so you get spontaneous breaking of time translation symmetry. You give this discrete time crystal, which in principle can evolve for extremely long times. So here we show this for S equals 40. This shows the case where you have zero interaction, you get tunneling, the lifetime goes down, and so on. And you get some coming back, again giving you this bump. And if you apply an interaction which is large compared with the critical interaction, it just continues on forever. Okay, so Ryan and Jar did the big complete calculation using a multi-mode quantum treatment for the case S equals 2. And this calculation is for a maximum quantum depletion, studying the quantum depletion as a function of interaction here, interaction strength. And you find that there's no loss of atoms except at the critical point. You get loss of atoms, which you don't work here anyway. So there's no quantum completion essentially, except at this critical point, or any heating out to at least 2000 miracycles, which is much larger than you could do in an experiment. And the system we chose for the experiment is atomic, it's potassium-39, it's 93% abundant, it's stable, nuclear spin, and so on, and it's a bosonic atom. It has D1, D2 lines, are very convenient wavelengths for our lasers. But most importantly, it has a beautiful, what we call Feshbach resonance, which is if you plot the interaction between the atoms, or here it's called the scattering length, versus a magnetic field in the right region, which is 402 Gauss, you get this dispersion-shaped distribution like this, which enables you to tune very, very precisely into tune the interaction between the atoms. So potassium is a particularly nice system for that reason. And the mirror that we oscillate is a repulsive light sheet, which means it's on the blue side of the resonance line for potassium. It's a green 532 nanometer laser. So the team, the experimental team I show here, we have Andrei Sidorov, who's here, Aparna's a PhD student who's close to finishing, Shamali, another PhD student, and Ali has submitted his thesis. Chris is from Krakow, who spent a year working with us, and Satoshi Tojo, he's from Tokyo, he spent a year sabbatical working with us. I'm very proud of the fact that of these 7 people, we have 7 different nationalities. So we have a lot of diversity, including women and men. Very proud of it. So the experiment, the Swinburne experiment looks like this, very complicated. It's a 3-dimensional optical table. We have other optical tables with all the lasers on, but this is just the actual experiment part. So we start off with a 2-dimensional magneto-optical trap, which is that little glass cell you can just see there, that little one there. And we have, that produces a beam of cold atoms, which we load into the main 3-dimensional magneto-optical trap here, and you can see a little red spot, that's the trap. And if we zoom in on that, it looks like this. So here's the magneto-optical trap, the atom's trapped in here. So I should say that we have multiple overlapping beams. In fact, it's 28 beams all overlapping in here. There's 12 beams at the D2 line, which is 767, 12 beams of the 770 nanometer D1 line. We have 2 beams of 1064, which we use for the so-called optical dipole trap. And the mirror is 532 beam. And we have an imaging beam on top of all that. So we have 28 overlapping beams in this tiny little region here. That just gives an indication of the degree of difficulty. Okay, so the signature for one of these big time crystals, big meaning S is large. We've chosen as an example S equals 40, where we have 40 wave packets. For no interaction between the atoms, we get tunneling between these different wave packets, and this just shows as a function of time after 55.5 bounces, 55.25, as the atoms bounce up to the turning point, hit the mirror and come backwards and forwards like this. We then apply an interaction using our Feshbach resonance, and it becomes a very nice stable system. You no longer have any tunneling, and this is your time crystal evolving backwards and forwards here. So this is an article on time crystals into the real world of condensed matter, which Krzysztof and I were asked to write. This sort of summarizes the applications that we have in mind. First of all, we have 2 knobs which can provide flexible control of the time crystal in the time domain. We have the driving of the mirror, f of t, up and down here, and we can vary the Fourier components of the drive and engineer effective lattice potentials for a broad range of systems or different types of experiments. Secondly, we can modulate the scattering length with the Feshbach resonance. And we can vary just by varying the magnetic field. It's very easy to modulate a magnetic field with any shape you like. And in particular of interest is when 2 wave packets cross paths during a bounce, for example, and if you tune the interaction so that that occurs just as they cross each other, you can engineer exotic long-range interactions in time lattice. And this shows an example of an exotic interaction, where interaction goes most positive and negative like this. One of the first applications is Anderson localization. First of all, for non-interacting system, and if you apply some disorder to the mirror, temporal disorder, you can get Anderson localization in time, which is a result of destructive interference between different multiple scattering paths. And this shows a calculation on a log scale up here versus the number of mirror oscillations for different times, t equals 0, then 510 oscillations, and then 20,000 oscillations, and it's completely frozen in here. This is well known in space, but we want to do this in time domain. That's for the case of non-interacting system. But in the case of a many-body system, which is interacting, you get, and if you have strong enough disorder, you can get what they call many-body localization in time. And this is a very interesting phenomenon, which is not well understood in space, let alone in time. And you get suppression of DC transport and extremely slow dynamics of correlation functions. So the next topic is topological time crystals. How are we up for time? Have 5 more minutes? Okay. So topological time crystals have become very topical with quantum computing and so on, because they behave as insulators in the bulk, but they possess conducting edge states, topologically protected edge states, sort of symmetry protected near the surface. And the proposal is, which Krzysztof Sacha was heavily involved in, was to do this in time, in the time domain, rather than in space. For example, we have a single particles resonantly driven with 2 harmonics now. This could give you a time crystal structure with a 2-point basis. You get 2 energy bands, which can be described by the famous SSH model, this is a tight binding model with staggered hopping tunneling amplitudes. And if you now apply a narrow barrier in the form of a periodic kick in time, this is introduced in the effective potential. This can give you bulk states, but more importantly, you get these two edge states coming up here, located in the energy gaps of the insulator. So it's an insulator for these edge states, insulator here and conducting states on the edge. And then very interestingly, there's a possibility of 2D time lattices. I showed you a very simple one before, of atoms bouncing between two mirrors, which are oscillating. But here, they're bouncing between two mirrors which are oscillating, but are at 45 degrees rather than 90 degrees. And one of the mirrors is in the direction of gravity, and the other is off gravity. And so if you have atoms bouncing backwards and forwards here, at this point when it bounces, the momentum is changed from the x direction to the y direction. And at this point, x goes to minus, the momentum in the x direction goes to opposite direction in x, and y goes to y. And as a result of this, if you look at the torus here, you get a flip at this point here, and this flip gives you a temporal Mobius strip. And with a Mobius strip, with appropriate use of the appropriate values of the parameters for the oscillating mirrors, you can get different types of two-dimensional structures. And here, this is an example of a honeycomb time lattice here. The blue regions are minima where the atoms sit, or a Lieb square lattice here, which is this one. And it's possible, in principle, to get other structures as well. So to summarize, first of all, we're a driven BEC system. The theory says we should be able to get big time crystals, meaning 20 to 100 lattice in a one-dimensional system. Two-dimensional should be able to do better than that. To allow condensed matter physics to be extended to the fourth dimension, time, we can get higher dimensional time crystals in 2 dimensions and 3 dimensions in time lattices. And by having a spatial lattice, which we call an optical lattice in space, we can have a time lattice on each of the lattice sites in space, and you can get time-space crystals. And it's been shown that you can even should be able to get 6-dimensional time-space lattices, as Krzysztof Sacha's shown. So potential applications, well, this is all very early days and it's really speculation. With applications to condensed matter physics in the time domain, this may open up possibilities for new novel materials, exotic phases and phase transitions, possibly storage devices in time and time space, where you now have extra dimensions. Maybe you can be able to store more information this way. Might be able to have timetronic devices, and this has been looked at very carefully by Krzysztof Sacha, where you can have temporal transistors analogous to electronics. And of course, there's a possibility in quantum technology because of these, for example, topologically protected quantum states in time. Quantum states are notoriously fragile, and looking for ways of protecting them. So in finishing, I'd like to thank Swinburne for giving us the opportunity to do these wonderful experiments when we moved from CSIRO 20 odd years ago, and also to thank CSIRO for being such a wonderful place to work for, especially in the first 20 years in things where we had a wonderful group with Alan Walsh. And finally, I'd like to thank my family. My wife Kay is here for their support and encouragement, and for putting up with me all this time so that I could follow my interests. So with that, thank you for your attention.
Thank you so much. Wonderful talk. Learned a lot, and also just really loved seeing all of the. Is this right? Can you hear me? All of the faces and people that we know, and understanding where everybody sort of fits into your grand plan of getting a Nobel Prize. So this is really fantastic. So now we've got 10 minutes or so. Please feel free to ask any questions that you might have of Peter. We'll also take reflections. So let's start with questions though. Okay. We'll just wait for the mic because we've got online people.
Hello, thank you, Peter. Great talk. Congratulations on the Companion of the Royal Australia Medal. I just had a question with the when you're generating these time crystals. Does that, if you've got this periodic driving that you're doing, if you stop that driving, does that time crystal continue to oscillate, and sort of what does the decay look like, or does it rely on the presence of that driving force to continue existing?
Yeah, it's a very good question. It doesn't continue. The ideal time crystal is what Wilczek proposed, where you start off with no motion and it spontaneously develops into an oscillation. And everyone said, oh, this is impossible, and so on, as it's turned out. But there are certain regimes where this might be possible, and Wilczek himself is still spending a lot of time working on this. And there are systems, for example, what we're talking about here is closed systems. But you can have an open system where you're driving with a CW laser beam, and then you can produce oscillations from a CW laser beam. But that's really cheating because it's not a closed system. It's interacting with the outside world via this laser beam coming in. That's just one example. And there are others as well, which are a little bit similar. But what we want is a closed system. And there's still possibilities, but we're a long way away. Thank you for the question.
Thank you. Other questions? Carl.
My understanding is the time crystals oscillate but don't possess kinetic energy. Could you explain that?
That is the million-dollar question. It's a very good one. And a lot of the theoretical work that's been going on is in the US, and they've dealt with a disordered system. And they have claimed that to stop this heating and so on, you need to have disorder with many body localization, which goes with the disorder. It's got to be fairly strong disorder to give you many body localization to stop the sort of the spread of energy and the thermalization. And they showed that for the conditions they used, which weren't ideal, they weren't rigorous conditions, they showed that with many body localization caused by disorder, you can stop the heating and heating up and losing the time crystal. And everyone, well, many people around the world have followed this approach and say this is the answer. But in the work that Krzysztof Sacha has done, he's shown you don't need disorder. All you need is periodic driving of any system, essentially. Provided you satisfy the right conditions, you can still get a similar effect, and a similar effect of no heating by the driving and no thermalization. And again, this can't be proved for the usual system of driving. This can't be proved rigorously that the time crystal lasts forever, goes to infinity, theoretically. But he's now come up with a system which Jar and Brian, and more importantly, just as importantly, Krzysztof Sacha, working on the paper at the moment, shows there is a system where you can show this rigorously. And that is if you have atoms moving around a ring, and if you have a rotating lattice that goes around with it, you can show that when you transform to the rotating frame, that there's no time dependence. So that when you then transform back to the laboratory frame, the system lasts forever. And this is an article just writing with submitting to PRL, which is very exciting, and I think it will answer all the questions from the US theorists.
The system has constant entropy.
I'm sorry?
The system has constant entropy.
Yeah. It's the all-important question. Thank you. We don't understand it properly still. Maybe Krzysztof Sacha
Peter,
want to say some more that
what
he knows
about,
a lot more about it than me.
Peter?
Yeah.
That's me. Yeah. What about the scattering from the lattice? The time lattice is like the scattering from a spatial lattice. For the spatial lattice, you have this direction and the back scattering and so on. And for the time, maybe I don't know about the energy and also metrology. What is your opinion on that?
Yeah. Again, Krzysztof's working on the theory of this, where you use Bragg scattering of atoms to, instead of having an oscillating mirror, you can transfer momentum to the atoms to give you an oscillation effectively via Bragg scattering. So that theory, would you like to comment on that?
I didn't catch the question. I'm not my cup.
Okay. Did you want to repeat the question?
Okay, sorry.
So are you asking about the possibility of making a spectroscopy of the crystal, or?
No, I'm talking about the scattering from the time crystal. It's similar to the scattering from the spatial crystal. So you can then, just like the Bragg scattering, then you can just select the right energy because not in time, rather than momentum or wavelength.
It's full analogy. You can slightly change the parameters of your scattering, but you have full band structure.
So that then you can select a certain energy and also do some measurement energy more precisely. Yep.
Any last questions? If not, we will thank, can you hear me? I mean, I'm on, but maybe you can't hear me. Can you hear me now? Anyway, I'll just shout. Let's thank Peter. And before we do that, we will be having some refreshments outside. So please do join us. It's time to reminisce, all the stories, anything that you'd like to say to Peter, and just catch up with each other. So let's thank Peter so much. Oh, sorry, before we do, I know you're poised to clap. Once you've said thank you, I'm going to get Peter to stand here and take a photo. So please don't move. So thank you, Peter. Yes, you may clap now.